Welcome to my series of videos on statistics, and in this particular video, I'm going to teach on the Fisher's least square significance difference test. All right. Now, one of the things I want you to know is that whenever you are dealing with the randomized block ANOVA, and then the test of difference of the mean, the test of difference of the mean hypothesis is rejected, like the instance in the immediate past video. All right. We have such an instance in the immediate past video where the test of mean itself, all right, the normal between samples, the test of mean was rejected, not the between blocks, but the between samples, all right, which told us that the samples do not have the same mean. When it happens, we have to check which of the samples is causing the difference. And when we are under the randomized complete block ANOVA, we use what we call the Fisher's least significant difference test to test which of them is causing the difference. So here, what I want you to know is that even if the null hypothesis of equal population means is rejected, the ANOVA does not specify which population means are different. So here, whenever we are dealing with randomized block ANOVA, we use the Fisher's test to test which of the groups is causing the difference, all right? When it is the normal ANOVA, that was when we use the 2K primer, the critical range test of 2K primer, right? But here, when we are dealing with a randomized block ANOVA design, we only test whether there's a difference among the pairings. We only pair them like 2 by 2 to test which of them is causing the difference. We use the Fisher's test. Now, what is the formula for the least? What is the formula for the Fisher's least significant difference test? The formula is your T statistic, okay, multiplied by the square root of the mean squared within, okay, multiplied by 2 over B. Remember, B is the number of blocks. Now, anytime we are reading T statistics, we will need two things. We will need the level of alpha, and then we will need the degree of freedom, all right? Now, for this particular test, the degree of freedom of the T is K minus 1, which is the number of groups minus 1, multiplied by the number of blocks minus 1. So in the example we solved in the former video, the number of groups were 3, so 3 minus 1. And the number of blocks were 14, so 14 minus 1. So here we have 2 multiplied by 13, so the degree of freedom is 26. So keep this in mind. And then our alpha level is 0.05. So it means that because it is two-tailed, alpha divided by 2 means every LSD test is two-tailed, all right? Is two-tailed. So one of the tails obviously will be 0.025, all right? Then the two tailed combined will be 0.05. So let's go and read our table. So this is the T value table. So for the T value table here, only one, so here we have one tail, right? So only one of the tails is 0.025. And then the two of the tails combined, because we are testing at alpha of 0.05. So that will be the two tails combined. So I'm going to look here, all right, this particular column as against a degree of freedom of 26. So here we will have a T value of 2.056, a T value of 2.056. So remember that the T value is 2 points. So the T value we are looking for here is 2.056, all right? Now, in the immediate past example we solved, the mean squared within was 9,850.9. Okay, also keep that in mind. All right. Then the number of blocks, we had 14 blocks. Then we have 2. So here, if you fix them in the formula, okay, if you fix them in the formula here, the T statistic, as we've mentioned, is 2.056. Okay. So if you fix them in the formula, the T statistic is, so in the formula, we have the T, that's 2.056, multiplied by square root of the mean squared within, that's 9,850.9, multiplied by square root of 2 over B, the square root of 2 over 14. But the formula is the T statistics, okay, times square root of mean squared within times square root of times square root of 2 over B, all right, times square root of 2 over B. So that's all that we are doing. So if you multiply everything, you get 77.11, all right, 77.11. Now, how do we check whether there is a difference? So here also, we are going to do multiple comparison, all right. So if you remember, we had 3 groups, and these were their averages. Okay, so I'm going to find mean absolute difference or absolute mean difference. All right. So here, group 1, its average was, remember, was 793.57. So this minus this. So group 1 average minus group 2 average. When you ignore the negative, you are going to get this value here. So this is exam 1 versus 2. All right. The next one will be exams or group. So exams 1 versus 3. Then the third one will be exam 2 versus 3. All right. So we are finding the absolute mean difference, the absolute between the absolute of the difference between the averages. So this minus this will give you exam 1 versus exam 2. This minus this will give you exam 1 versus exam 3. And then this minus this will give you exam 2 versus exam 3. Okay. So once you do that, you are going to get these absolute differences. Okay. These absolute differences. So we are going to compare these absolute differences against the least significant difference. So here we only have one thing that we'll be comparing the 3 things against, all right? So here, since this one is less than this, of course, it means we will not reject the null hypothesis that there is no significant difference. That means that there is no significant difference between the average of exam 1 and the average of exam 2, all right? The second one, 125.57, is greater than the least significant difference. So it means that we will reject the null hypothesis that there is no difference between exams 1 and exams 3. Then we will conclude that there is a significant difference between exam 1 and exam 3. Then finally, if you compare the absolute difference between exams 2 and 3 to the least square difference, it is great. So definitely we will reject the null hypothesis and conclude that there is a significant difference, all right? So the second part of this video, I'm going to teach on how to use the Excel. When you have data, I'm going to teach on how to use the Excel to run the analysis for the blocks, all right? So let's go to our Excel. So let's use this example. Let's use these figures as an example. So we just go to data analysis, all right? Now, if you are going to do, we are going to do ANOVA for randomized complete block analysis of. So we are going to do, when you're going to do the randomized complete block ANOVA, you choose the ANOVA 2-factor without replication. ANOVA 2-factor without replication, all right? Remember, you choose ANOVA 2-factor without replication, and you go to OK. So as we normally do, we will select our data span. I think my Excel has automatically selected it for me, but I can do it manually. So I can select, use my, so when I put that 9, I'll hold my shift and use the arrow keys, the forward arrow key to choose and come down here. All right. So that is all. I'll now press OK. So when you press OK, you have these results. You have these results. All right. You have these results. All right. What is more important is not the summary, but the ANOVA. Okay. Now, in these results, okay, let me show you something. In these results, remember this slide. The total here is the total within variation. So please, this result doesn't give the sum of squared total. The total here rather gives the total, it gives the total of the within variation, or what we normally refer to as sum of squared within. Right, so this figure here, the total here is rather sum of squared within. Okay, then the F values here, the first F value is for checking whether blocking is effective. Then the second F value here is the main factor test. Okay, so let's go to our Excel. Let's do some interpretations. In our Excel, let's go to our Excel and do some interpretations. So as I said, just a moment. Okay. Okay. So as I said here, this figure here is the sum of squared within, all right? But much more importantly, the F here, listen, the F here is the hypothesis testing for blocking, all right? And then the second F here is the normal hypothesis testing for the ANOVA itself. So this is the F, and then this is the critical F. So here, since the computed F is less than the critical F, okay, we fail to reject the null hypothesis and conclude that the blocking is not effective. All right. We fail to reject the null hypothesis and conclude that the blocking is not effective. And then the second one here is for the normal ANOVA, and it's more than the critical F. So we reject the hypothesis and conclude that significant differences exist, okay, between the means. So it means that there's a significant difference between exam one. Sorry, here there were 4 columns. This is not the exam. See here, if you remember our data, there were 4 columns. So it means that significant difference exists between column 1, column 2, column 3, column 4. But of course, later we are going to do the least square difference test to check which of them is causing the difference. Now let's remember the formula for the least square difference test. This is the formula for the least square difference test. So let's assume, all right, let's assume that we are testing it at alpha of 0.05. That means that we first of all need to get our degree of freedom. So remember, our degree of freedom in this instance will be k minus 1 times b minus 1, okay? So there were, in this example, this particular Excel example we are solving, in this particular Excel example we are solving here, the number of groups were 4. There were 4 groups, all right? 4, and then the number of blocks will be the horizontal. So we have 5 blocks. So like this is a block, this is a block, this is a block, this is a block, this is a block. So 5 groups and then 4 blocks. 5 groups, 4 blocks. So the number of groups were, sorry, 4 groups, 5 blocks, sorry. So it is 4 groups, 5 blocks, okay? The number of groups were 4 minus 1. Then the blocks is 5 minus 1. So here we have 3 times 4, which is what? 12. All right. So we are going to read our T table. Degree of freedom of 12, and we are testing at 5% level. All right. So we are going to do the same reading. Degree of freedom of 12, but we are testing at 5% level. So 5% level means each tail is 0.025. So degree of freedom of 12. So here, degree of freedom of 12 here. So the T is 2.179. All right, so the T is 2.179. The T is 2.179. So we are using the same formula to check whether there is a difference. So the T is 2.179. Okay. The T is 2.179. All right, the T is 2.179. Then remember that I told you that in the Excel, all right, in the Excel output, okay, in the Excel output, what is here? This figure here is the sum of squared within. So if you want the mean squared within, you have to divide the sum of squared within by its degree of freedom. All right, you have to divide the sum of squared within by its degree of freedom. Okay, we're going to divide the sum of squared within by its degree of freedom. You get the mean squared within. All right, so that is 231.8 divided by 19. That will be 12.2. So 231.8 divided by 19, that will be 12.2. All right, so in the formula, this one times the square root of 12.2 times the square root of 2 over b. So 2 over, we had 5 blocks. All right, so we are going to punch this 4.8136. When you punch everything, you're going to get 4.8136. So here again, we are going to do group 1 versus group 2, group 1 versus group 3, and all that. All right. So this particular question, we've already done the group difference calculations already. All right. So if you remember, the mean of group 1 was 10.8. All right. We solved this, this example way earlier. Okay, we are just using it for, so the mean of the group 1, we have mean of group 2, so you can just refer to the former videos. So here we can find the means of the groups. Okay, we can find the means of the groups, these groups. We can find their mean. So we have mean of group 1, mean of group 2, mean of group 3, mean of group 4. All right, so if you remember, so mean of group 1 minus mean of group 2, absolute. So 10.8 minus 13, we had 2.2. Then group 1 versus group 3, that was 10.8 minus 9, we had 1.8. Then group 1 versus group 3 was 10.8 minus 15.6. We had 4.8. And then so this is group 1 and 2, group 1 and 3, group 1 and 4, all right? Then we now started with, so this is, the first one is group 1 and 2, the second one is group 1 and 3, the third one is group 1 and 4. Then we came to group 2 and 3, that is 13 minus 9, which is 4. Then group 2 and 4, that will be 13 minus 15.6, that is 2.6. Then group 3 minus 4, that's 9 minus 15.6, absolute. So all the figures are absolute, we ignore negatives, all right? and that was 6.6. We are going to compare these figures to the least square, the least. We are going to compare it to the least significant difference and then make a decision, all right? So the least significant difference that we have computed is 4.8136, okay? So 4.8136. So here we know it will run throughout, unlike the 2K test, right? So here 4.8136, 4.8136, 4.8136, 4.8136, 4.8136. So when we compare, this is less than this. So it means that we fail to reject the null hypothesis that there is no significant difference. That means that there is no significant difference. 1.8 is less, so no significant difference. 4.8 is also less, so no significant difference. 4 is also less, so no significant difference. 2.6 is less, so no significant difference. 6.6 is greater. So yes, there is a significant difference. So after controlling for blocking, there is a significant difference in group 3 and 4, right? Now, the disclaimer I'm giving is that calculations may be prone to error, okay? So please just focus on the main idea and use your own calculation to punch. If you're having different figures, you can give it in the comment section so that other viewers can follow, all right? So this will bring us to the end of the ANOVA analysis. Kindly subscribe, share, comment, and most importantly, subscribe, okay? In the next video, I'm going to teach on some other interesting things. So you are going to meet in the next video. Thank you very much for staying with us, and kindly subscribe to the channel. Thank you.